Well, there are just few subjects which I would like to discuss before we would learn actually what are the principle of operation of an engine. And with a pretty good approximation, engines which we use operate on an almost ideal gas, because in those cylinders we usually have gas which performs the work. Well, almost exclusively, yeah, because I mean, even if we put a gunpowder somewhere, it is still that the gas created in the explosion will perform work. So I would like to spend a little bit of time still talking about ideal gas. We had already defined ideal gas through the macroscopic picture. Recall that ideal gas is a gas which obeys particular equations. A product of pressure and volume is proportional to temperature and the amount of gas. On the microscopic scale, ideal gas, well, is a system in which all particles are identical. The number of particles is large, so actually it is that practically all the time there are particles which are in contact with the walls or with the piston. Now it is that the distance between the particle is large compared to their size. It means that they don't interact a lot. That the particles move randomly. Well, they move randomly, obviously, following Newton's laws. So until they interact with each other, they practically move along a straight line over there. And they practically do not interact except for collisions. Now, recall that collision is a very brief interaction. Well, on the microscopic way, in the microscopic view, it must be very brief interaction, because it means that most of the time the particles cannot interact. Practically, fact that they collide, it means that they cannot really store energy in a form of potential energy due to interaction with each other. Actually, I found on the internet, I found a nice simulation of an ideal gas. So I'm going to launch it. Hopefully. Have I launched it or not? Let's try again. And actually, I like this simulation because this simulation was also showing how. Oh, I think we are getting there. What happens actually when we change volume of that gas? Okay, let's try to access it a different way then. How about if we just copy that link? Okay, good. Now the colors actually don't mean that the particles are of different that they are different time. Really, they are the same time. So actually, I would prefer the colors really represent what is the kinetic energy of individual particles. Really, the picture should. Oops, how about that way? Yeah, all particles are identical. So now that color scale does not distinguish what energy particles have. Now, all right. Now, depending on this, what kind of speed the particles have, they will have a different temperature. Now, how about if we actually take? Can we take fewer? Probably not. Fewer molecules. Oh, here it is. Let's eliminate. So now you can see that interaction is very brief, and well, particles almost travel well half-third of the. This is really a very good picture of an ideal gas, where the separation between the particle is about that. It's interesting also to see what will happen if we indeed think that the gas is in a gravitational field. Yeah, because now I will turn on gravity. On the right-hand side, we have gravity, and I want you then. How about if I make actually this a little bit hotter? How about if we make it really strong? Now, what do you observe here? Can somebody notice something? That there is a gradient of distribution. We have higher concentration of molecules at the bottom and lower concentration of molecules at the top. Now, pressure, well, can you see that the gas exerts a force on the walls? How? Through what? Through the collisions. Yeah, the gas also interacts with the wall. So look at this picture and figure out on which wall actually the gas exerts stronger force, on the bottom wall or on the top wall? On the bottom wall. Yeah, not only that the particles over there move faster, but there is more of them hitting the wall. Now, what does it really mean? Express it in terms of pressure. Think about how pressure is distributed. Where pressure is higher, at the top or at the bottom? At the bottom, right? The force exerted, because in this wall, we see that the force exerted at the bottom wall must be greater than the force exerted on the top wall. All right. So let's now go back to the lecture. And well, I want you to take a look at the microscopic picture and calculate actually what affects that pressure. And from that ideal, from that model of an ideal gas, microscopic model of an ideal gas, we will see that we will come up to the conclusion that product of pressure and volume is indeed proportional to temperature for the type of gas which I just described on the previous one. Well, we will have to go back to a point which we well, this picture already existed a long time ago when we introduced concept of pressure. And now recall what pressure is. Gas also produces hydrostatic pressure, which means that there will be only one component which is non-zero. Well, three components which are really non-zero, but they are equal. And the remaining components are going to be zero. Which components are zero? Let's name them. It's a long time ago. We discussed this picture a long time ago. So which components are going to be zero and which are going to be equal? all shearing components are going to be 0, which means that the forces exerted parallel to the walls are going to be 0. Now, forces exerted perpendicular to the walls are going all to be equal. Now, let's say that the size, I won't now mark it as a differential. It doesn't matter if it is differential size or finite size, and it also doesn't matter if you think that outside we have the remaining gas, or you can think about it that this is a container holding the wall. Right now, we will try to figure out what kind of force the wall has to exert on the gas to keep it. This will give us the value of the pressure. Now, the force exerted by this wall results from the fact that the particles collide, right? So when it moves, it hits the walls, and whenever it hits the walls, it changes its momentum. If this is an elastic collision, it means that let's say that we consider this wall. So the only component of momentum which changes is x component of momentum, which means that this wall exerted a force in the x direction. And well, I will let's start with this, that we evaluate average force exerted by one particle, average with respect to time. Well, I will use impulse momentum theorem. Well, the particle changes its momentum from, let's say, initial momentum which was to the right to momentum which is to the left, and x component changes into opposite value. Well, so if x component was mv initial, then the change in momentum, magnitude of the change in momentum will be twice that big. And the force, average force which a single particle exerts on that wall will be, I will have to divide now by, well, how often it hits. So just one collision will change momentum by this time, which means that the impulse which was delivered will be average force multiplied by the time between two collisions. Now, how much time does it take to have two collisions? The particle has to travel, I mean, between, let's say that it collided, so it has to go back to the other wall and back. Well, if it was traveling with speed, with velocity whose x component had that value, which means that, there shouldn't be this square. It's a mistake. So don't copy that. The distance which is traveled, it is 2 times the separation between the wall divided by the x component of the speed with which the particle travels, which means that now the 2 and 2 cancels. This expression will go to the numerator, so I will have square of the x component of speed. So this is the average force exerted by a single particle on a wall. Well, let's now think about the pressure. So from the definition, I will have now to divide force exerted by all particles which collide with the wall by the area of the wall. Well, single particle exerted this force, which means that in order to find force exerted by all particles, I will have to add average forces exerted by all particles constituting the system. This expression says that I have n particles inside of this block, capital N particles. I can see that mass is a constant, this distance is a constant, so I can take it in front. So I will have mass divided by volume of this cube. And well, here I have to add squares of x component of velocities of all particles. Well, I can think about it that if there are n particles, so rather than having all of them, I will multiply number of particles by their average x component of velocity. Now, x component, if I add x component of velocity plus y component of velocity, square of y component of velocity plus square of z component of velocity, what am I going to get? Well, I will get square of magnitude of velocity. So I will get square of speed. Now, there is no preferential direction, so an average square of velocity in each direction has to have the same value, which means that square of x component of average velocity plus square of y component of average velocity plus square of z component of average velocity will be just 1/3 of the square of speed. So instead of having this expression over there, I wrote that it is average speed. Yeah, oh, notice that over here I have square of x component, average value of square of x component. I express that as a square of average speed divided by 3. So now n is here. Instead of a cube of the size, I wrote volume, and I multiply and divided those two, the expression by 2, so that way I got this expression here. Now, what does this expression mean? Why did I put actually that 2? Because now we can recognize that this is average kinetic energy of a part of a single particle. Right? So, it means now that pressure is directly related to the kinetic energy of the gas. Actually, I have a volume over here, so I can multiply both sides by, how about if I do it here? Let's start with this expression, and I can multiply both sides by volume, and I will have that product of pressure and volume is 2/3 times number of particles in the system multiplied by average kinetic energy of a particle. Now, if I look at the macroscopic definition of an ideal gas, product of volume and pressure is supposed to be equal number of moles of that substance, which really is a number of particles expressed in Avogadro numbers, times gas constant times temperature. So okay, now I can recognize that this expression gives me the total kinetic energy of all particles. So if I multiply both sides by 3 and divide by 2, I will get that the total kinetic energy of all particles constituting that system is equal to 3/2 times number of moles of the gas times gas constant times temperature. Well, since there is no potential energy associated with those particles, which it means that that total kinetic energy of the particles is the internal energy of particles. Actually, it is a very important statement about an ideal gas that internal energy of an ideal gas depends only on temperature of the gas and the number of particles. It does not depend on volume or on pressure. All right. I want now to spend a little bit time on molar heat capacity of an ideal gas and make a conclusion about what really gas constant mean, that number R. If I take a look at the isochoric process, I can recognize that amount of heat which I deliver to the system will be equal, I mean, if in an isochoric process, temperature is going to change. Therefore, I can express that heat delivered with the in terms of change in temperature. And, well, for any system, whenever I relate heat with change in temperature, the proportionality coefficient between these two is referred to as heat capacity. So I have to write down heat capacity. And I will express that heat capacity as the number of moles of the substance multiplied by molar heat capacity. I use here subscript V to indicate that this process is an isochoric process. Now, in isochoric process, if we take a look at the first law of thermodynamics, I can recognize that the amount of heat is equal to the change in the internal energy. Why? Why in isochoric process? I mean, we have already discussed it once. Why in an isochoric process change in internal energy is equal to the heat? Because when volume is constant, how much work does the system do? None. The system does not perform work, which means that the change in the internal energy is equal to the heat. So I can write down that this amount of heat is equal to the change in internal energy. Well, which means actually if I integrate both sides in appropriate limits, I can also write down that internal energy is equal to heat capacity of the system multiplied by temperature. Internal energy is proportional to temperature. Now, for the gas which we discussed a moment ago, and that gas contained, this was a gas of individual particles, so we saw that internal energy was number of moles times 3/2 times R times T. So from that previous slide, I can conclude that for this type of particles in an ideal gas, the molar heat capacity at constant volume is 3/2 times gas constant. Gas constant has a certain value, which means that this ideal gas will have a particular molar heat capacity. Now, if I take a look at the process in which pressure is maintained, internal energy now will be affected not only by the heat delivered to the system, but also by the amount of work with the system, which the system is performing. Because in order to maintain pressure, we would have to allow the gas to expand. And if the gas expands, it means that it performs work. Temperature will also change, which means that I can relate amount of heat delivered to the system with change in temperature by heat capacity. And I express heat capacity again in terms of number of moles times molar heat capacity, but this time I put symbol P here to indicate that the process is at constant pressure. Well, from first law of thermodynamics, I can express this amount of heat delivered, that it is change in internal energy plus work done by the gas, right? Because first law of thermodynamics says that the change in internal energy is equal to heat minus this work. So I moved that work to the other side. Now, in an ideal gas, change in internal energy depends only on temperature, and here we have how it depends on temperature. It does not matter what kind of processes, because internal energy is only a function of temperature. So although I wrote it on the isochoric process, but the reason for the isochoric, because then it was easy to relate temperature with internal energy. But since it is valid in every situation, I can copy that expression. From ideal, from the equation of state for an ideal gas, recall that P times V equals nRT. So if I differentiate both sides, I will have, with constant pressure, so I will have that P times change in volume is equal to nR times change in temperature. So from an ideal, from the equation of state, I can express P times dV as nR dt. I did this because really what I want to do is I want to find out how molar heat capacity at constant pressure is related to gas constant. So I'm expressing everything in terms of change in temperature. Every term over here is expressing in terms of change in temperature. So I can make now a conclusion that molar heat capacity at constant pressure, I mean this expression, because now I can take out dt, and I will have N CV plus R. So molar heat capacity at constant pressure is equal to molar heat capacity at constant volume plus gas constant. So which molar heat capacity is greater, at constant pressure or at constant volume? Which one is greater? Look at the expressions here. With constant pressure, heat capacity at constant pressure is greater than heat capacity at constant volume, which means that in order to raise temperature of an ideal gas, we have to deliver more heat if the pressure is constant. If we keep pressure, then if we heat it up with maintaining the volume. Why? Think about conservation of energy. Yeah, because heat, when we deliver heat, we deliver energy to the system. And now, what that energy is used in each of those processes. When we have, when the process is isochoric, that heat is converted into what? Anybody will volunteer to say? Or how about you? What? Can you?
Pressure.
When we deliver, no, I mean pressure is not something which refers, is measured in joules, so some form of energy. Yeah, so if we deliver heat at isochoric process, all that heat is converted into, it is true that that the pressure will increase. Not temperature, temperature is not measured in joules. Kinetic energy and really in thermodynamics, correct. So it is converted into kinetic energy of the gas, right? Which we refer to, if we look at this microscopically, this will be the internal energy of the gas. So when we heat gas and maintain its volume, all that heat is converted into internal energy. Now, how about isobaric process? Can anybody think about it? Can you?
Well, then there's work done to change the volume.
Aha, right. So some of the heat is used to into internal energy, which results in raising temperature, and some of that energy is used by the gas to perform work. Well, so conservation of energy, from conservation of energy, it should be obvious to us that indeed amount of heat which we deliver when the gas performs work must be greater than if all of that energy is converted into internal energy, which is proportional to the temperature. All right. I'd like to talk now about a process which is, we refer to this as an adiabatic process. And adiabatic process is defined as a process in, we have already discussed what is an adiabatic process. It is a process in which heat is not delivered to the system, which means that internal energy is associated only, or is dependent only with on the amount of work which the system performs. So change in internal energy in the adiabatic process is opposite to amount of work performed by the gas. Now, amount of work performed by the gas is equal to the pressure of the gas multiplied by change in volume of that gas. On the other hand, I recognize that the change in internal energy of an ideal gas depends only on change in temperature. I can write it down that this is heat capacity of that gas multiplied by change in temperature. Now, from the equation of state, now in an adiabatic process, both, if we look at the equation of state, on the left-hand side we have product of pressure and volume. So now when we calculate, when we try to differentiate this product, we have to use product rule. So it will be, pressure times differential of the volume plus volume times differential of pressure. And on the right-hand side, we have only temperature, which is variable, so we will have change in temperature. Now I can eliminate from these two equations change in temperature and derive. Actually, what I want now to do is I want to relate how pressure and volume are related when process is adiabatic. This is my goal. So really I manipulate the equations which I know to express pressure as a function of volume. So by eliminating temperature from those two equations, I have already an equation which involves only pressure and volume. So now I can solve this equation for pressure. This equation, unfortunately, is a differential equation. However, it is an equation for which it is relatively simple to solve by separating variables. I can move now pressure on one side, all expressions which contain pressure on one side, and all expressions which contain volume on the other side. And if I do it, I will have such an expression. Because I could group, here I have pressure times differential volume, and here I also pressure times differential volume. So I group these together, and I have differential of pressure on this side, and then I divided both sides by product of pressure and volume, so it cleaned up. I have a constant times differential volume divided by volume, and I find it that this is opposite to differential pressure divided by pressure. Now I can integrate both sides in corresponding limits. This is a constant. This expression is a constant, and when I integrate dv over v, what function am I going to get? Natural log of v. And over here I will have dp over p. If I integrate that, I will get natural log of p. And we will have to plug in appropriate values. Now, I recognize that this is molar heat capacity at constant pressure, right? Because it's molar heat capacity at constant volume plus gas constant, so this is molar heat capacity at constant pressure. Here I have molar heat capacity at constant volume. That quotient is very often represented by a symbol gamma. Well, I can now take this gamma into logarithm. Yes, I would have to raise logarithm. I will have, and this minus also there, also into the logarithm. So I will flip the quotient over here. So logarithm of this expression raised to gamma is equal to logarithm of inverse of this expression, which means that the arguments are equal. So if the arguments are equal, I can come to the conclusion that product of pressure and volume raised to the quotient of molar heat capacities at constant pressure, at constant volume, is not changing. This equation now relates pressure and volume. And how about if we compare it to an isothermal process? In an isothermal process, instead of gamma, we just had 1, right? Now, gamma is a number greater than 1. So if this was an isothermal process, in an adiabatic process, pressure would drop faster versus volume. So if I expand system adiabatically, pressure drops faster than in a process in which we maintain temperature. Now we can understand how an engine works, and I wanted to start with an engine which goes through the most efficient engine, or a process which is most efficient. We don't have engines actually which operate that way. We didn't construct them. The engines which we use are less efficient than engines based on the cycle which is referred to as a Carnot cycle. And in a Carnot cycle, if I draw now, I will draw the processes on the indicating pressure versus volume. Carnot cycle contains two isothermal processes and two adiabatic processes. So let's say that we start with a small volume. What we have to do now is to increase the volume using isothermal process. So this is a gas at relatively, we will see actually if we want to have temperature high or low. But if gas expands in isothermal process, it means that we have to heat it all the time. So in this process, heat is being delivered, gas expands, but the temperature stays constant. If I take a look at amount of work which is done, it will correspond to that area over here, right? Now the next process is an adiabatic process. And in adiabatic process, pressure drops faster than it would in an isothermal process. So it drops now down like that. It means that actually that piston would have to be connected to some kind of a flywheel. So the flywheel really make it to expand further through an adiabatic process. And it gets to this point. So gas expands even further, right? This is amount of work which is, this would be the amount of work which was done. What we do next is compress the gas performing along an isothermal process. Well, it means that actually that flywheel will have to push the piston now to squeeze this gas. However, squeezing the gas occurs at lower pressure than expanding of the gas. In an isothermal process, we would also need to take away some of the heat. Now, the work in this process would be negative. Actually, it is that the gas would take away some of the energy of the flywheel. So actually, we will lose this amount of energy. This was negative work. And finally, in order to come back to the initial state, we choose another adiabatic process from state D to back to state A. So this gray area now represents the amount of work or amount of energy which was converted into work. In the entire cycle, the system performed more work than it absorbed energy. I mean, in form of work. It performed more positive work than negative work. I mean, it's not accurate, but probably the most intuitive. Do you understand me? Yes, so when the important thing is that when the gas expands, we have to keep high pressure. When the gas compresses, we have to keep in the cylinder low pressure. And these two adiabatic processes actually switch between the two values of the pressure. Now, in an entire cycle, we came back to the same state, which means that the change in internal energy of the gas is zero, which means that the heat which was delivered in that process, and we delivered heat when during isothermal expansion, and we took away heat during isothermal compression, so the net heat was equal to the difference of those two heats. And this is the amount of work which was obtained. Now, efficiency of the engine is defined as the ratio of the amount of work which we got to the amount of energy which we put in. So the best engine would be such that it does not take any heat during this isothermal compression. Well, we don't have such a possibility, so we always have to waste some energy into this heat expelled during compression. And if we derive an expression for efficiency related to temperature, efficiency in a Carnot cycle depends on the cold and hot temperature. Ratio of cold and hot temperature determines how efficient is the engine. I was hoping actually to discuss one more engine, but I think that I'll do it in this case tomorrow. So let's end the lecture here. Thank you very much.